I'm a Roy Hong representing. So it's about time to IOM3 start this. I'm here to introduce the much rated tonight. We lecture Professor Material Engineering from the University of Michigan. Evening. Well, actually, please bear with me because I have a quite long introduction about our speaker tonight. For those who know relatively little about our speaker, please listen carefully, because tonight we have a heavyweight speaker tonight, not physically, but in terms of his research and academic achievement. So Professor Victor Lee is actually a very famous academia. He is the James Rice Distinguished University Professor Emeritus of Engineering, and also Wylie Collegiate Professor Emeritus of Civil Engineering at the University of Michigan. He is a fellow of the ASCE, American Society of Mechanical Engineers, the World Innovation Forum, and also the ACI. Actually, Professor Lee, his research interest is in multifunctional materials target for enhancing civil infrastructure sustainability and resilience. Well, actually, Professor Lee is a very prestigious scholar and also researcher. Well, there are too many awards I have to name in full, so may I skip this? But actually, perhaps one of those very prestigious awards is the Wylie Lifetime Achievement Award in 2016. Well, Professor Lee is also a very reputable scholar. His publications have received over 60,000 citations. He ranks the first globally among the top 2% highly cited authors in the building and construction materials by the Stanford University in quite a number of years. He, in the US, back in his days in the US, is also a quite popular researcher and academia in the media. Okay, actually, he was featured in the interview broadcast by CNN, CBS Evening News, Discovery Channel, etc. Okay, so the topic tonight is about engineering application of ductile concrete. ECC stands for Engineering Cementitious Composite, ECC. Well, for this material, it's our pleasure and honor to have Professor Lee to speak, because actually he is the inventor of this low-flow material. In fact, this material perhaps is now quite new to us, but actually it's now gaining momentum in the Chinese mainland. Okay, recently, actually, the Great Association in the field of concrete in China, they have recently established a subcommittee solely on this material, and they have the honor to have Professor Lee to officiate their inauguration of that subcommittee. So without further ado, may I invite Professor Lee to speak on this topic. Thank you.
Thank you very much. Can you all hear me from the back? If I may have some water, that would be good. Yeah. Okay, so let me first thank the organizers. There are a number of them here listed for organizing this conference or meeting or presentation. I actually have been working with this material for some years, and I've given a number of talks over the years, both here in Hong Kong and in mainland China, of course, previously before I retired, also in the US and other countries. But I understand that there are a number of from industry participants here. So I'm going to focus, and I was also reminded that I should finish my talk early enough to have dinner. So I'm going to skip over many of the theoretical aspects of the work. There is a very strong theoretical foundation, but you won't hear it from me tonight. But rather, I'll focus more on the application. So trying to answer the question, okay, you have this funny bendable concrete, as some of the media would describe it. Who cares? Why is it useful? What's the difference from conventional concrete? What's the difference from high-strength concrete or ultra-high-strength concrete, UHPC? Well, hopefully I can answer some of those questions. That's the the meaning of this, the motivation behind this talk. So let me take a step back and very briefly give an overview of what has happened to concrete. Concrete is not a static material. It has been undergoing development over the last 100 years or so. You can see some of these here. The creation of reinforced concrete, pre-stressed concrete, obviously is an attempt to overcome the fact that concrete is brittle. It's hard to build structures, especially large-scale structures, without the use of steel to carry the tensile forces. So these developments have enabled concrete to be used and become industrialized on a large scale. Now, later on, high-strength concrete, typically high compressive strength concrete, has been going on for some years and continue to go on now in some laboratory, ultra-high strength concrete, creating concrete with higher and higher compressive strength, reaching about 200 megapascal, for example. Self-consolidating concrete, I was lucky enough to be in Tokyo on one of my sabbatical leaves when self-consolidating concrete was created in the laboratory at the University of Tokyo. And they invited a lot of industrial participants, somewhat like what we're doing here. And that become industrialized first in Japan, and then later on in Europe, and still later on in the US and in other places. More recently, self-healing concrete trying to reduce the impact of damage, geopolymer concrete, carbon capturing concrete, trying to obviously reflect our desire to go green in construction, right? So all these developments are extremely important, and it is what brings concrete from 100 years ago to now, okay? Now, what you might have noticed is that concrete over these 100 years of development remains brittle. It cracks, okay? And what we're trying to do with ECC, or Engineered Cementitious Composites, is to make a ductile concrete. Okay, you're going to be the judge. Have we succeeded in creating a concrete which is ductile? Possibly reducing or even eliminating steel reinforcement in certain circumstances. Okay, so let me answer the question. Well, we have steel reinforcement, so why bother? Why worry about tension? Well, we see in these pictures collapse of buildings under extreme loading, large earthquakes, and more ordinary times we see this kind of deterioration of reinforced concrete. And as I mentioned, nowadays we are very concerned about carbon emissions. So these problems remain, even despite the fact that we have a lot of developments, but the fact is concrete remains brittle. Okay, so what does brittleness of concrete bring to us or cause us in terms of problems? I mentioned earthquakes, so you can see here actually a shear crack in this supporting pier on the lower floor of a building, despite the steel reinforcement inside. You obviously do not want to live in this building where the earthquake happened. And on the right-hand side here, you see this kind of cracking on floor slabs is very, very common. And then water, or in the case of US, we use a lot of de-icing salts. That chloride ion goes in and attack the steel and cause deterioration. So we have on one hand, issues with the lack of resiliency in our infrastructure and the lack of durability, okay? And so these two are important issues that we need to address if we are going to further advance our field. Okay, so what we set for ourselves is, as a goal, is to develop a new modern concrete that exactly attack this brittleness problem of concrete material. Can we make a ductile concrete? Okay, to be honest, I was told many times when I was in my younger days as an assistant professor that, Professor Lee, you are being stupid. You're wasting your time. This is foolish. Concrete has always been brittle. Thank you so much. And you can't change that. That's the fact of life. Again, you'll be the judge. And you can answer that question later on, towards the end of the seminar, to see if we have succeeded in creating a ductile concrete. Now, what I want to precede before showing you the ECC in details is to say a few words about material development testing. So we want to make sure that the concrete as a material is tested under as much as possible near the field conditions. Okay, that is more realistic. So for example, in contrast to that, very often in laboratories, we see permeability study of concrete intact, a disk of concrete in the lab, and trying to create a hydraulic pressure, force water through and collect on the other side. That is a measure of permeability, all right, but does it represent reality? In the field, we have loading and cracks associated with that. We saw that a moment ago. When you have cracks on a bridge deck slab, for example, water just go into through the cracks, right? They don't care how tight it is, how dense your concrete is. It doesn't really matter. The water and the chloride ions and any aggressive agents just find the weakest point, that's where your crack is, and go in. So test under field condition. Even if you cannot go into the field because sometimes it's not practical, you try to simulate field conditions. You try to load the specimen before you actually apply the hydraulic pressure and then measure permeability. I'll show some of those in just a moment. But that's what I meant in this line here. Cost, right? I was often asked about cost. Cost of material is obviously important, but it's also important to think about the cost to the created structure itself. What's the difference between cost of material and cost of structure? Of course, the cost of material get translated into the cost of structures, but structures also have dimensions. Say a pavement slab, for example, has thickness and has steel reinforcement. What if the property of your concrete allows you to get away without steel reinforcement or a thinner slab? That makes a big change. And what is important here in this example is that you want to measure the cost per, let's say, square meter of pavements, as opposed to the cost of the material itself per cubic meter, for example, right? So that's what I want you to keep in mind. Similar idea about carbon emissions. And there, we also need to think about both the short term, which I would label it as embodied carbon in the material or in the structure just after installation, but also the long term. The long term, because service life of our infrastructures can go anywhere from 20, 30 to 100 years, right? That's a very long lifetime. And if you have a durable structure, you cut off a lot of those repeated repairs. And that means a lot in terms of carbon emissions. So we also need to think about operational carbon. This word here, okay? Embodied and operational carbon. I'll come back to detail these just to give some background idea to keep in mind for now. Okay, so again, the question we want to pose to ourselves is, can we design a new modern concrete that allows these desirable characteristics in our infrastructure? What are they? Infrastructure resiliency under extreme loading, durable in the field conditions, and sustainable. Can we put all of those in one single material? Why do you insist on one single material? Because it doesn't really mean very much if you have a very resilient material that allows you to create a very resilient building, but it's not green, it's very brown or very dark, right? Or if it's not durable and require repeated repairs. That's not very good. And same idea if you skip the resiliency, but make very durable structures, but it's not safe. That's not very good, right? So the question is, and you might think this is obvious, right? But if you look at research work done around the world, most research are done just for one of these three things. Okay, so that's not very good. We want all these three characteristics to be enabled by one single material for infrastructures, leading to infrastructures that are resilient, durable, and sustainable. All right, so here is the ECC that you have been waiting to see if you have not seen this before. This is normal concrete, brittle under bending load. So you have elastic behavior and suddenly it fractures into two pieces. We are all familiar with that. But in ECC, you actually allow the material to undergo plastic deformation. I put it in quotes because it's not actually like steel plasticity, but it is damage tolerant. If you look very carefully on the underside of this slab here, there are micro cracks on the bottom. So the material is damaged, but despite the damage, the composite remains low carrying. It doesn't give up, okay? In that sense, it looks like metal plasticity because after you have bent a steel to beyond the elastic stage, it can still have low carrying capacity. And that's the reason, one of the reasons why we value steel as a structural material. It can go beyond the elastic stage. Now we have been able to create a ECC, a new version of concrete that have the same kind of behavior. Okay, so if you look from the viewpoint of a tensile stress strain curve, let's say a specimen loaded in direct tension, a piece of concrete will behave like this, elastic, and then suddenly the crack forms and the load drops to zero. Okay, so it completely gives up low carrying capacity. If you put some fibers, which has been around for some years, fiber reinforced concrete, you have this tail here. So you have tension softening where a crack opens up, and as it opens, fibers bridge across, and they often break or tensile pull out of the fibers, so the low carrying capacity continues to drop, okay, while the crack opens up larger and larger. In ECC, we have this funny behavior. You have an elastic stage, and then it undergoes strain hardening, tensile strain hardening. And you can see that despite the damage that I show here, the material low carrying capacity continues to rise. And how far does it go? Well, for this illustration, it shows about 3 to 5%. We can actually do even more than that. 3 to 5% is very large strain deformation. That's the reason why you saw that bent specimen smiling at you in that shape. And this is because the material can undergo very large deformation. Compared to normal concrete or FRC, it undergoes this softening or sudden collapse at 0.01%. So we are talking about not just a few times more ductile, but hundreds of times more ductile. Okay, so this is what we call tensile ductility, a ductile concrete. We have a stress strain curve that resembles that of ductile metal undergoing strain hardening behavior. All right. So that was an illustration curves to compare different material. This is the actual test curve of one ECC material. This is a normal strength ECC, which shows about 4% tensile strain. And I also included a UHPC material, which has higher tensile strength and compressive strength, reaching about 8 megapascal before it fails. When it fails, it shows this very rapid softening, better than normal concrete because of the steel fiber typically included in UHPC. So the value of this is very high compressive strength. And we were often asked, can you actually make high compressive strength ECC? And the answer is yes. So several groups now beyond our own research group. So this picture, I believe, was taken from a group at Tongji University. But there are many other groups now that have been able to produce ECC with very high compressive strength. And the tensile strength remains like this. So it has very ductile, maintains the high ductility. And this is achieved with a now newly available fiber, PE fiber, which has now gone substantially down in cost. It used to be a novel material which is interesting academically, but now it becomes affordable. It becomes real. It is actually used. And I'm going to show you some examples of applications, as I promised. So a little bit more about the damage behavior of these materials, the same elastic and then strain hardening behavior of a ECC. And what I'm showing you here on the right y-axis here is the crack width development. So this is very interesting. Notice that as I increase the strain in this tensile specimen, the cracks width start to increase, going from 0 to about 60 micron here, okay? And then what is very interesting is that if you continue loading, keep pulling and stretching the material all the way up to 4% strain here, the crack width remains about constant. How about that? So even at large deformation, the cracks remains very tight. And this is done by itself. We are not using any steel reinforcement. This is intrinsic property of ECC. ECC has the intrinsic behavior of having tight crack width, even though you deform it to a very large extent. Okay. Now that is very important, and I emphasize that because it's critical to durability of infrastructures. You see that durability, or conversely, the degradation of infrastructure is strongly related to the width of cracks in the structure under surface. Okay, this is I hope this short video shows. So the tight crack width is obviously valuable for durability, but it also have this interesting characteristics that if the material or the infrastructure is exposed to air and rain, this is what happens. It repairs itself. Okay. So self-healing of the material. All right, so let me quickly jump to talking about the 3 characteristics that we value. We want high durability in our infrastructure, damage tolerant, and creating resiliency in our infrastructure, low carbon footprint, both embodied carbon and operational carbon. Let me show you the details, a little more detail with also illustrated with examples. Okay, so let me start with durability in self-healing. So this is the chart that I mentioned a moment ago, plotting the level of degradation against crack width. Some of these are our own data, but others are collected from the literature by other research groups. But no matter which kind of degradation we are talking about, water permeability, chloride ion diffusion, corrosion of the steel bar inside the material, and so on, it doesn't really matter. They all show this interesting behavior. Look at what happened. At very low crack widths, below 100 micron, 0.1 millimeter is 100 micron, below that level, the change is very little, almost flat, these curves, which means that at very tight crack width, degradation almost is non-existent. The material behaves as if there were no cracks at all. It doesn't see the presence of the cracks. However, once you pass the 100 micron mark, threshold, if you will, suddenly all these curves shoots up, okay? Degradation goes up very, very fast. They are not linear. They respond to crack width in a very highly nonlinear manner, okay? And what is interesting here is I also put this mark here, this blue arrow here. That's the old ACI, American Concrete Institute, the standards, the building standards. And there was an old limit here, which no longer is present now in the new code. But it used to be there, and I'll explain why that changed in a moment. But here, what is interesting here is that if you design your structure and make use of steel reinforcement, typically that's what you do, and try to keep your crack width to below this level, then if you are successful, it should be relatively low, although it's starting to go up even in this range, right? But if you are just a little bit off, whether it's in your design or in the environment the infrastructure is exposed to, you will be on the right side of the arrow, which means that your degradation is very high, which means that for structural engineers, it's really very difficult to control. The reliability is very low because that's a small change. You get either a very good, high quality, durable infrastructure, or just a little bit, you get an infrastructure relatively new but requires repair early on in life. Okay, and that exactly is why ACI eliminated, because structural engineers said, I can't really reliably design my structure that way. Okay, so there is no longer in the new code, the new versions of the 318 code, this requirement of crack width. there is a change to number of rebars and their spacing. And that's it. That everybody can put in and measure the distance, and you can satisfy that. So you are not at risk of your engineering license, right? But it doesn't really actually cure the problem. The problem remains here in terms of durability. So the reason why I'm showing you this chart here is that in ECC, and you saw that a moment ago in the test curves, the crack widths are intrinsically controlled to less than 100 microns. The stress strain curves, the stress crack width curves are all showing less than 100 microns, 60 microns. So it's in this range. This is intrinsic in ECC. You don't have to count on steel reinforcement in order to achieve high durability. Okay, so if you ask what's going on, why is that the case? If you look at the permeability measurements, and I'm going to stick here some, I promise Professor Poon that we will have dinner. You actually get ECC at very low permeability despite the preloading of the specimen, put it in tension, and then expose it to a hydraulic pressure and measure the permeability. You see that the ECC is all in the low 10 to the minus 11 meter per second, compared to concrete, which can have all different kinds of crack widths. And then you see the permeability going up really fast. This is not a linear axis. This is a log axis, right? Every unit is a 10 times, 10 times, 10 times jump. It's going up very, very fast. And that explains what I just showed you a moment ago. Now, that's permeability, but you can, you can do the same kind of study with regard to chloride penetration. And we did this, again, deliberately loading the specimen under bending before putting it to an exposure to a chloride solution, high concentrated chloride solution. And you see that the effective diffusion coefficient responds to preload deformation. For the mortar, it goes up very, very fast. With the increase in crack width as you bend the specimen, the chloride diffusion rate goes up very high. In ECC, it also goes up, but in a more like a linear fashion. And this is because as you increase the load and cause larger and larger deformation, the crack number increases, but the crack width stays constant. You saw that a moment ago. Crack width, despite large deformation, remains low in ECC. That's an intrinsic property. Okay, so these two test curves, and I'm going to jump over this one. They are demonstrating in the laboratory, simulating field conditions, the reason why ECC can be very durable for infrastructures. Okay, so let me jump to real life applications. That's what I promised at the beginning. This is a very early application in Japan, carried out by one of my former students. He's leading a team of engineers at Kajima Corporation. You can see the date there. So it's over 20 years now. So this application involves the use of ECC for a surface coating of a dam which was leaking. And there was erosion of the old concrete. And the repair was done by shotcreting ECC on this layer. And it has remained just as good as before, so after 20 years. This is another application much closer to now. It's a couple of years ago, I believe. And it's carried out in Sichuan in China. So I ran into Dr. Li Yong a couple of months ago, and he showed me these images he took. This is a use of ECC, again by shotcreting ECC as a tunnel lining. Okay, and what he discovered is that these are some of the parameters that you can see. But what he was pointing out after a few years of experience is that this ECC tunnel lining remains watertight. Okay, and it demonstrate high resiliency against earthquakes, and durability and crack control, and even control of the surface finish, which they like to have. So these are some advantages, and the reports after a few years of use remains very good. And this, some of you in the audience recognize that. This is me, believe it or not. This is a tunnel lining, actually it's a cave-in. And the idea is to use ECC as a single pass permanent lining. And there are a number of reasons why this study was carried out in Hong Kong. One of which would be a much higher speed construction, reducing the amount of time of construction. In Hong Kong, you all know, time is worth a lot of money. So these are some, whoa, I forgot that I have a video. So this is spray ECC. All right, so back to mainland China. This is another application carried out by one of my former students in Tsinghua University. Professor Zhang unfortunately passed away during COVID, but the work was continued by one of his former students now in this Bridge Research Center. And the idea is to use ECC as an upper layer, the top layer of this viaduct, particularly at locations where the slab experiences negative moment. So you have tension on the top layer, and ECC is very good in taking tension, so that's why it is used there. So this was carried out in 2021, and it remains very good. I spoke with this, and then another example of similar kind. So this one here, I feel like at least I should show you something from the US, since that's where I have worked for many years. But this is an interesting use of ECC. And incidentally, an example of comparing ECC with UHPC and a non-shrinkage grout that they have been using is a study carried out by Virginia DOT in 2018. And Dr. Selig told me that they have problems with leakage of their typical grout, which is used to grout the connection between these steel box beams fit together by shear keys and used as a bridge slab overall. And they get water leaking through these joints and cause durability problems. So they were looking for a solution, and in this study, they used their conventional grout, their UHPC and ECC. And what they reported was that ECC was the only grouting material that did not have any sign of leakage. All the others have leakage problems. And it's not surprising, UHPC is very strong in compression. But in this application, compression doesn't play a role. It's crack control. It's crack width control. Okay? It is shearing the keys, but shear in a 45-degree orientation turns into tension, diagonal tension. Okay? So this is obvious, you would say, and I agree with you. Once you have a problem with tension, tensile capacity, not compressive capacity. This is an early use in Japan of ECC on a composite bridge deck in Hokkaido. It's a beautiful site. So there is a steel plate on the bottom, and they overlay the ECC. And in this case, what is interesting is that there are no expansion joints. It has been in operation for, I believe, 20 years. I forgot to put the date there. So again, early use, and hence demonstrating durability of ECC. Now, I have to admit that it's not like 100 years of experience, but this is a relatively new material. So these are some of the images I have in my possession that shows infrastructure a little bit longer in usage. Okay, but so far so good. Okay, so now let me switch to structural resiliency. These are recent pictures. The ECC is used now in many parts of mainland China in this context. Many of the houses are built as masonry, and these often do not meet the design code requirement. Okay, so they are under danger when there's a big earthquake, and the government is very concerned. So they require retrofitting, not repair, but retrofitting, upgrading the seismic resistance of these houses. Okay, And there are lots of them. And people are living inside, so it has to be done in a very quick manner, okay? So let me see if I have more pictures like this. Here's another one here. This is a different location in Xi'an. And you can see the use of ECC on the outside of these walls. I was told that there are now over 4,000 cases, 4,000 houses already retrofitted. So ECC is no longer to many in mainland China, ECC is no longer a novelty. It's something that they are using, okay? And they are upgrading the quality and hopefully save lives during the next earthquake. Now, it's not limited to small houses. These are actually earlier use of ECC in tall buildings. I have been to these buildings. This is in Yokohama, near Tokyo. This is right in the heart of Tokyo. And these are very nice looking buildings. And the ECC is used to enhance the building to resist large earthquakes. This one here is in Osaka. It's a 60-story building. At that time, the tallest residential tower in Japan. And by making use of ECC, and I believe I have a picture here, in these coupling beams in the core of the building, it actually reduced the cost of these buildings and construction much faster at higher speed. Now, this is a test, some of the many tests that was carried out before they were used, or before they were allowed to use. So this is a fully reversed cyclic shear loading of the beam in the middle, okay? And it's compared with regular reinforced concrete beams. So you can compare the two after the same kind of loading, fully reversed cyclic loading. The full reversal is responsible for the 2 sets of diagonal cracks, okay? And with the reinforced concrete, you see that the cracks become so large that they expose the steel reinforcement, whereas the reinforced ECC have very tight crack widths. In fact, if the student did not paint the micro cracks, it's very hard to find them. Okay, some of you may be interested in the hysteresis behavior. The RC beam behaves like this, and our ECC beam behaves very differently. It maintains the peak load to a higher level compared to the peak load here. So it delays the failure. And then even after the peak has been reached, you can see how stable the envelope is, the hysteresis envelope, as opposed to rapid dropping of the peak load in the hysteresis. So this maintains stability of the structure, even though it has already reached the peak load. And of course, energy absorption as characterized by the area under these hysteresis loops, right? Much bigger than the pinching behavior in reinforced concrete. These kind of tests is what gave rise to the structural engineers in the confidence in actually using this ECC material in full-scale buildings. I don't mean to say it's very easy, but they actually were very, very careful and go through many, many different tests. And I didn't have time to show you, but they also go through fire tests and so on before they are allowed to use. So it looks like this. The ECC coupling beams were used 4 pieces on each floor. And this is in the building core. And by the way, one of the driving force behind this design compared to what they had before was the fact that they put all the load carrying element in the core of the building, in the center core here. So the outside part has very little structural elements. And I actually went up to this top building before it was completed. And I was very impressed once I exited the elevator, temporary elevator. It was just sheets of glass. Everything has no blockage of views, no big columns, because everything is in the core, okay? That was one of the driving force. And this building, after my visit, I was told that Professor, I don't think your salary can afford a unit here. And I have to agree with that. It's a very expensive. But if you ever visit Kitahama in Osaka, there's a station there, subway station there. You exit at Kitahama subway station, and then you go upstairs. That's the building. Okay. Okay, so these are the coupling beams. They were created in precast yards before they were installed on each floor of the building. So I took this picture. So these are the coupling beams and the elevator shaft inside there. And that's what it looks like. Okay, it's a beautiful building. Now, let me switch to another use of ECC. Again in Japan, along the East Coast, a viaduct runs along this coastline here. Now, I show you this example because of the fact that this is a very good example where multiple functions, characteristics of ECC were utilized. Guess what they were? Obviously, you would say high seismic resistance is important. It's in Japan. It's in Japan. So that's the easy guess. But what else? What else is important in these applications besides seismic resistance? Look at the right-hand side picture. Corrosion, right? Coastal exposure to an aggressive environment. So look at this seawater here, right? So this is salt water. It's running along the east coast of Japan. So they had used steel as dampers to try to reduce the relative motion of the deck, of the bridge deck, sitting on the piers. What they were worrying about is relative motion was so big during an earthquake, it just drop off, right? So reducing this relative motion is important, and they used the concept of dampers to reduce this. Steel dampers were used before, they all corroded. Okay, so they use ECC with no steel, and that's what it looks like. So that's about 1,000 pieces of these ECC dampers were used along the many kilometers of the viaduct. All of them precast in a precast yard and brought to site and installed. You can actually see the installation. So it has actually two components. One looks like a T shape, and the top part of the T is anchored into the pier. So it's becomes part of the pier. The bottom part of the damper is like a pocket, okay? And it's anchored onto the top of the pier, okay? So the two things, they interact with one another. When the deck try to move, this portion becomes like a beam, okay? It's undergoing bend. It's blocked by the pocket below. So it reduces the relative motion. That's the very simple concept of creating the damper. In this case, it's making use of the structural resilience, damage tolerance of ECC, as well as the tight crack width, leading to durable infrastructure. Both of these are important in this application. Okay, I can't avoid this. This is not a big structure, but I really like it. It's shared with me by Professor Yu Jiangtu in Tongji University. And he created this, what he called a wormhole in a pavilion in Shanghai. It's very pretty looking. And what is interesting from a structural viewpoint is that there's no longitudinal reinforcement in this sculpture, if you will, structure. Okay, so it was tested by very heavy steel balls, and they passed the test and then created it. But it looks very pretty to me. Okay, so let me switch over now. I talk about structural infrastructure durability, infrastructure resiliency, and now I switch to infrastructure sustainability. Okay, and focusing particularly on carbon emissions. So just in case you missed what I defined earlier, embodied carbon is the carbon emission associated with either the material during the production of the composite, the ECC, or the installation of the structure at the beginning of service life. That's what I define as embodied carbon. Operational carbon is after your structure is put to use, okay? And then it undergoes repeated repairs. Those repairs causes emission because of new material usage, because of the traffic congestions created as a result of repair requirements and so on. Okay, so this comes at a later stage of the life cycle of an infrastructure. This comes at the beginning stage of the life cycle. And embodied carbon, let's start with the material itself. So I will be the first to admit that when we first created ECC, we created M45. Okay, another was in the research group in those days. But M45 becomes a more or less standard material. Lots of groups doing studies. It's actually very good in terms of durability and in terms of damage tolerance, ductility. But when you measure the carbon footprint, it's not very pretty. It actually went up a lot. And it's easy to understand why that is the case. We eliminated the coarse aggregates and replaced it with cement. That's terrible, right? And then we use plastic fibers, synthetic fibers, which is made from crude oil. So it's a double whammy in terms of carbon emission. That's why it went up so much. Okay. But since then, a lot of different groups, including our own, have studied different versions of ECC and essentially brought down the carbon emissions to about the same level as normal concrete. Okay. In fact, this last point here was created by one of my latest students just before I retired, now in Taiwan, at the University of Taiwan, National Taiwan University. And he was able to drive down the carbon emission to below that of normal concrete. The secret is to use very low carbon binder. So some of you may have heard of the LC3 binder, the limestone calcine clay invented by Karen Schriffner in Switzerland, at least popularized by her. But that was not that was very good. But for some time, that was the only low carbon binder available. But in my last visit a few months back in mainland China, 2 of my former students have started companies, developed and commercialized low carbon binders based on waste material. And these are already now available. So low carbon binder is used. Some of these ingredients are recycled, and carbonation curing is also used during the hardening stage of the ECC material. When you combine all those, it's possible to drive down the carbon footprint. So this is embodied carbon of the ECC material at the beginning stage of the service life. Now, what about if you move from the material to the structure? Okay, so I have only calculations for this very simple structure. This is a reinforced concrete pipe with steel reinforcement inside. And compare that with a ECC pipe, and notice that for the ECC pipe, because of the tensile ductility, it does not require steel reinforcement. So we remove the steel reinforcement, and we thin down the wall thickness, okay? Reducing the wall thickness, as a result, reducing the amount of material required. And yet, with these changes, elimination of steel reinforcement, thinning down the pipe wall, it actually performs better under diametric loading. Instead of brittle collapse into quarters, in the case of steel reinforced concrete, it actually deformed into an oval shape. And what I don't have time to show you is that we also did permeability studies. So we put water inside this greatly deformed pipe. The water did not leak. Amazing, we were surprised. Now, what I really want to show you is that if you compare the carbon footprint of these 2 structural elements, very simple structural elements, if the concrete is 100%, then the reinforced concrete is 100%. The ECC pipe is reduced to about half of that. Okay, how is that possible? You say, how is that possible that you have a material that is supposed to be less green, even if we say that it's equal in greenness at least you get a pipe that should have the same amount of carbon emission, but you get 50% off. Well, we remove the steel reinforcement, we reduce the amount of material required. So in order to achieve this, it is important to think of ECC as a material that should be used with proper design of the structure. You don't want to replace conventional concrete with ECC one-to-one and don't make any changes. If you do that, then it typically raises the carbon footprint and it raises the cost. Okay, so this is an example where I want to emphasize that you really need good structural engineers to appreciate how the material behaves and use that in the design process to reduce the amount of material as well as and you typically carry out by the modifying the geometry, okay, and possibly removing steel reinforcement. Here's another example, okay. So this is comparing conventional concrete pavement, which shows the cracks there, and this piece here, we use a ECC to replace the conventional concrete pavement. In this case, on the surface it looks the same, no difference, but inside we actually reduce the thickness of the pavement by 50%. Okay, why is it possible to do that? Because the flexural strength of ECC is more than double that of normal concrete. Okay, so no steel reinforcement, lower thickness, in fact, no expansion joints, no cut joints required. The material ductility takes care of that. Okay, so it also reduces the cost, labor cost and reliability. Reducing 50% in thickness brings down the cost, brings down the carbon emission. So this is reduction of embodied carbon at the beginning of the service life, this example of the pavement. Okay, what about long-term behavior? Okay, so I need to use an example that was done many years ago. In fact, I believe 2005. This was the very first test of ECC in the field, and it was carried out in collaboration with the Michigan Department of Transportation, MDOT. So they expressed to us that they experienced problems and cost in both performance and cost because of the failure of the expansion joints on bridge decks. And they need to repair those joints every summer, which was expensive to them. So what they want a more permanent solution. And what we suggested is to remove the expansion joint, the steel expansion joint, remove some portion of the adjacent concrete slab, and replace the whole thing by a ECC link slab. Okay, why do we want to do that? Let's see if the schematic shows. ECC is stretchable, it's deformable. So it serves the function of an expansion joint when temperature goes up and down. Okay, it needs to stretch and it needs to contract, and ECC has no problem doing that, right? So it might have micro cracks, but they are very tight. Okay, and so it serves the function of a joint. But if you ever drive on this bridge deck, you will say to yourself, there is no expansion joint. Why? It's because it's so quiet, right? When normal expansion joints, when you ride on it, it goes boom, boom, boom. Every time your car, the wheels hit the expansion joints. You don't have that anymore. It's completely quiet. It's like on the surface, like a continuous deck, except for the slight color difference. So here it is. So this was on a bridge about 15 minutes from my office when I was in Michigan. And the on-site casting, we used 7 truckloads of ECC cast to create this link slab. And these are the dimensions here, and just reopen to traffic. If you ever visit where I used to live, I no longer live there, but you will be using this highway from the airport to Ann Arbor in Michigan. And your car will go under this. So these images I borrowed from Google map, and it shows the ECC link slab still in good shape after this 20 years or so. Okay, now I showed you this example, not so much for durability, but the fact is that durability drives down the emissions of carbon in the operational phase. And that's exactly what this graph is showing. So conventional bridge deck and the ECC link slab deck reduces about 40%. Much of it comes from these two colors. The red color is delta traffic, and it's easy to understand that because you have less repair, you have less emission, tailpipe emissions by cars that needs to detour to get around the construction site. But what was surprising to some was that the yellow color also it becomes smaller compared to this yellow color. This is material, okay? And at that time, ECC was not green at all. ECC was very brown, as I mentioned. The M45 is not very, very green, not green at all, I should say. So how is it possible that we have reduction even on the material aspect of the calculation? Well, again, because we have less repair events, and therefore you end up with less amount of material required over in this example, 60 years of service life, okay, using this calculation. So you end up having a lower amount of emitted carbon in the operational phase. Okay, so just to summarize, I talked about durability, and it's led by the fact that ECC has very tight crack widths. It's very durable in many different environments we have tested. I don't have time to show that. Some of you may be interested to go deeper. I'll show you, hopefully I have the book. There's a book I wrote on ECC, which summarizes all of these, the details. You can find them there. But essentially, durability of infrastructure is brought about by the fact that ECC has very tight crack width control by itself, not depending on steel reinforcement. Okay, so this is important. Now, high damage tolerance, I have mentioned many times. So this is what leads to enabling of resilient, highly resilient infrastructures against heavy loads like earthquakes. And then the last point is low carbon. I already mentioned that, so I won't belabor that. So it's possible to have all three characteristics, making use of one single material, ECC. Okay, so summarizing all these ideas, ECC material enhances infrastructure resiliency, durability, and sustainability. Notice that I keep emphasizing infrastructure resiliency, not just high strength material. I emphasize infrastructure durability, not just laboratory durability of a small piece. Okay, and infrastructure sustainability. Why do I emphasize that? Instead of just focusing on the material, I focus on the infrastructure. Because that's what we use. We use bridges, we use buildings. We don't use concrete exactly in our daily lives. Do you drive concrete? You drive on roads, right? We have this beautiful building. We have a seminar in a nice room here in this building. So we use the building. We are not using a concrete. So the building has to be resilient and should be durable and should be low carbon. Okay, that's what we really should drive for. Okay, so so far we have used the material, and obviously I don't have the time to cover all of it, but in summary, it's already used in the transportation industry sector, the water sector, the energy sector, and the building sector around the world. So a lot of it in Europe and in the US early on, but then moved to Japan, and now mainland China is taking up, and some applications also in Singapore. Okay, accompanying the adoption of this new material, and it's very necessary, are the creation of standards and users' guides. So there are already a number of these, both industry and regional standards in China, helping to drive an adoption of the material. In Japan, they published the very first user's guide of the ECC material, and the US also. So some of these things are interesting to look at. And our chairman, Roy, just mentioned the development the establishment of a subsidiary under CCPA, and I happen to be there. So you have the honor to initiate the establishment of this subsidiary. Just how was that ago? Maybe a couple of months ago in Guangzhou. So I guess this is the question in many of your mind. Is Hong Kong ready for ECC? Why is it not used? So I feel that, I mean, it does require some thinking, but I think the short answer is yes. Hong Kong is ready. There is no reason why not, if I want to put it that way. There are already 2 ready-mix plants that has experience in mixing ECC material. There are some limited amount of field testing of the material. I think there should be more, but I hope it's coming along. And what is also very important is that at least 4 universities, local universities here, have been doing research in ECC. And I think the fact that we have these human talents is extremely important. And we have that in Hong Kong, okay? So of course we need to have the research translated into applications, and that requires collaboration between academics and industry, okay? And I think we are at that juncture now. What kind of collaboration are we talking about? Transfer from basic research to the field, to the applications. We need local standards so that structural engineers feel comfortable to use this material, relying on standards, and developing a reliable supply chain of ingredients of the material. All of these things are important, but there's no reason why we cannot do it. Mainland China has started on doing this. Now, one of the obstacles, I might mention it earlier on, is the higher cost of the fibers, the synthetic fibers. And one of the better fiber to use actually is not PVA, even though we have studied that a lot, but it's a high modulus polyethylene fiber. And this used to be very, very expensive, but I ran into the owner of a relatively newer company who is now manufacturing at large scale PE fibers and supplying, he told me, to at least 2/3 of the world's demands now. They really scale up fast. But the good news is that he believes that he can drive down the cost for construction use to a level that is compatible and competitive with normal concrete. That's very encouraging, right? That's coming from industry. So supply chains problems can be resolved. I feel that we just have to work together to connect all these pieces, different pieces of the puzzle together, and not just allow academics like myself to talk about ECC. It's not good enough. A technology should be utilized, and our executive leader wants us to lead, right? And in the larger Delta region, we can. We have the people and we have the technology. And if I'm needed, I'm here. I was born in Hong Kong, okay, many years ago. I'm old, but I'm still a little bit useful. Hopefully. Okay, so much for that. So let me draw a conclusion. So I think you have seen in this presentation actual field use of the material. It's not just an academic study. The material has gone to various industrial sectors around the world, not just in the US, but also in Japan and other places. And the idea is that the material can be translated into enhanced structural durability and resiliency, and in many cases, increasingly improving construction efficiency, like reducing the amount of time for construction or tunnel lining, for example. Okay, reducing carbon footprint. In mainland China, this has become very, very important driver to green the technology, to green the industry. the construction industry. They really want that. And I think we can deliver also on that. Okay, so there are some standards and users guide that we can rely on, but I believe we should develop our local standards. Many of you in the audience have much more stronger expertise than I have in that regard. And I'm hoping that we'll see that happen very, very soon. So if you are interested in this topic and want to drill down a bit deeper, this book is already published a few years and it has been translated by my colleagues in different parts of mainland China, but led by a professor in Southeast University. And I was told that this has already gone into the second printing. So you can read either in English or in Chinese more about the details of ECC. A lot more than what I can describe in this short hour. I'll stop here.
So thanks very much, Professor Lee's very inspiring talk. Well, originally, it is now the time for Q&A, but unfortunately, I'm told that due to the scheduling of this venue, well, unfortunately, we are unable to take any questions. But I believe we practitioners, academic, government, etc., we will find Professor Lee, your expertise very useful. Not only you are a useful person. Okay. Okay. So perhaps I believe some of you may want to know more about ECC or other expert advice from Professor Lee. Perhaps we can, as an organizer, we can help share with Professor Lee's contact to all of you, so that in case you have any question or anything you want to know more, we can help you convey the message. So perhaps due to the limited time, how about we as an organizer to present our token of appreciation to our speaker, Professor Wylie, or how about Professor C.S. you also come to present this opening?
Thank you. Very kind. That's very pretty.